Hello, welcome back. So, the last few lectures I have discussed about the flotation chemicals in brief. Now, I will talk about the flotation machines in brief, that are the different types of machines available and what are the very purposes of these machines. I would just like to discuss that. So, flotation machines again, there are two types. One is called pneumatic cells and is called mechanical cells. So, essentially the cells actually how do generate the bubbles and how do enable the particles and your chemicals to be mixed properly, and how the froth phase is being created, and then how the froth is being transferred to a separate launder where you are collecting your separated materials. So, pneumatic machines are those which either use the air entrained during pulp addition or the air blown in or induced. That means, the pneumatic machines either use the air entrained during the pulp addition, because you will be having some entrained air, or artificially you are blowing the air in, or maybe the air can be induced. It generally gives a low grade concentrate and little operating trouble. Example are the Dabcra cell, flotation columns and the Jamieson cell. These are the varieties of designs, but they are basically the pneumatic cells. Mechanical machines are characterized by mechanically driven impeller, which agitates the slurry and disperses the incoming air into small bubbles. That means, in this mechanical machines, you have got an impeller and that basically rotates, and because of the rotation the slurry gets agitated. That means, you create a turbulent condition, so that your fluid phase, your solid and your chemicals, they try to get basically having a environment where they get an opportunity to be mixed properly with the collectors, and it also should disperse the incoming air into small bubbles. That means, it helps in bubble generation. An example is shown here, that is where you have got an impeller here, that is a rotor, and it rotates, and that is called a disperser. So, that basically disperses the bubbles, and how the bubbles are being generated. Now, the impeller may be your hollow, and through that you can inject air into that, and that air basically you have got a disperser, and that because of that your bubbles are generated. When it tries to go up, it will have, you are controlling the bubble sizes based on the your say the arrangement you have made here. And when you try to basically rotate it, this your rotor draws pulp upward. That means, it rotates like this and it creates a basically an turbulent atmosphere inside this, and the slurry would like to go up because you are trying to rotate it. Like if I take a bucket of water and if I put my hand into that, dip into that, and then if I rotate that water, you will find that the entire thing tries to go up. So, and along with that you are having a basically disperser, that is called a disperser, and then you are generating the bubbles and it disperses the bubbles also inside that. There are flotation columns. Now, that is another type of cell. It provides a means for improving the effectiveness of froth flotation process. It is also a froth flotation process, but the cell design is different with an aim to improve the effectiveness of the froth flotation process. These columns are typically 1 to 3 meter in diameter and 5 to 15 meter high. It is like a very huge column. The column could be square, circular or rectangular. They are sometimes baffled vertically into sections to promote better mixing. So, mixing is very important phenomena here. Mixing of what? Now, mixing of between the particles and your flotation chemicals. A column essentially performs as if it were a multi-stage flotation circuit arranged vertically. It means you have got stages of flotation arranged vertically, it is like that. With slurry flowing downward, slurry tries to flow downward, while the air bubbles travel upward, producing a counter current flow. That means, slurry is trying to go down and the air is trying to go up, so that you can have a proper mixing between them. It is a typical design. The basic principle of column flotation is the use of counter current flow of air bubbles and solid particles, so that my particle bubble attachment is much more effective. The counter current flow we have also discussed while discussing about your settling columns. The similar principle, but there were no bubbles, here we have got bubbles. Particle will try to go down because of its settling velocity, and the bubbles will try to go up because of its buoyancy, and if the bubbles, so the your interaction between the particle and bubble is much more higher, and the hydrophobic particles, they will get attached to the bubble surfaces, and if their settling velocity is lesser than the upward velocity of my bubble, they will be transported to the top. This is achieved by injecting air at the base of the column and feed near the midpoint. The particles then sink through a rising swarm of air bubbles. It is a very complex hydrodynamic situation, and basic aim is that your proper mixing between your bubble and particle attachment, or you are giving every particle or creating a situation where every particle has a chance to decide that whether I will adhere to the surfaces of the bubbles or not. That is dictated by the nature of those particle surfaces, that is whether they are hydrophobic or hydrophilic. There is a schematic of a column flotation cell. See that here the air inlet is there, there is a sparger, and through that air is basically purged into that, and you generate air bubbles. There is the feed in the form of slurry, and they try to, the particles will try to come down and the bubbles are trying to go up, and there you create a froth phase with your hydrophobic minerals, and then through that what you are doing, an additional feature here is that is called the froth phase. You add additional water from the top, that is called the wash water. It helps in dislodging the entrained particles in between these bubbles. That means, whatever the particles are entrained which may not be hydrophobic, but they are basically entrained in between your bubble, the void spaces in between the bubbles, and so that they can get dislodged, and then with the mechanism of like a wire flow through wires, the overflow wire, the froth phase is being collected into the concentrate outlet, we call it. And this is the pulp phase, that is between that. Pulp means is the solid liquid mixture, and that is the particles which are basically hydrophilic, they will sink, they will not get adhered to the surfaces of the bubbles, and that is the tailings. That is how we have a collection mechanism, that is called a tailings. So, this is basically another your say schematic and in a real one, that is a column flotation cell, the Cardici Metso site. We have I have taken it from them. I greatly acknowledge that, and that is how the feed is basically in the pulp form. The feed here, there is the wash water coming from there, and that is how the air is going up, and this is an interface between your pulp and your froth phase, and that is how the concentrate is being collected. This is your typical column flotation cell made by the Metso. The main advantages of columns, they include the improved separation performance, particularly on fine materials, because the residence time of the particle is much more higher. The gap between your froth phase and your pulp phase is much higher than in comparison to your normal flotation cells, and they are very good for particularly very fine materials, because fine materials you have got large surface area. So, it is very difficult to maintain selectivity of this. So, when it is because of the counter current flow principle and because they are dispersed enough, because of the degree of your turbulence you have created as a multi-phase your situation. So, it has been observed that you get a better separation performance or while dealing with very fine materials. It requires low capital and operational cost, because in one cell you are doing many stages. It requires less floor space, because you are using the height, and adaptability to automatic control. You can control each stage in a much better way than the conventional cells. The ability to build deep froths coupled with the use of froth washing make columns attractive as final cleaners, where the production of high grade concentrates is required. Now, if I make a comparison between the mechanical cells, that is the conventional cells, and the flotation column, these are the only the broad classification, that is your comparative your parameters. The mechanical cells work like an ideal mixtures, but flotation column they operate under conditions of plug flow with varying degrees of axial dispersion. Mechanical cells, the air bubbles are formed by a rotating impeller. In a flotation column, air bubbles are formed by passing compressed air or air slurry mixture through a bubble generator. So, you are using a bubble generator here. So, you can control the bubble sizes in much more effective manner than the mechanical cells or the bubble size distributions, to be precise. In mechanical cells, the relative velocity between air bubbles and mineral particles is negligible, except near the impeller, because near the impeller what is happening, because the particle mass is much more higher than the bubbles, the particle may have much more higher velocity than the bubbles, but in other zones it is almost identical. As chances of collision are reduced. Here the flotation column, the relative velocity between air bubbles and mineral particles is high throughout the length of the column, since they move counter current. Particle is trying to go down, bubble is trying to go up. So, the relative velocity differences are very high. Mechanical cells, at any given time, only a small fraction of the mineral particles is in the vicinity of air bubbles created. That means, they are dispersed based on their masses. So, the particles are much more towards the wall and the bubbles are away from that, but eventually when they, so That means, the effective residence time of particles is small compared to the total time of presence in the cell. In the flotation column, total length of collection zone is available for collision and attachment. The entire zone you are basically using it for your collision and attachment. So, that means, you are giving more time for the bubble particle attachment. Thus, the total residence time is effectively utilized. In mechanical cells, the detachment of once attached particles and contamination of froth by entrainment of non-floatable particles occur, because the way you are generating the bubbles by using your rotor, because of high shear forces, the detachment of your attached particles also can occur. In flotation column, there is a reduced possibility of detachment, because it is based on the counter current flow principle. There is no additional force you are using, so that the once they are attached, they will be detached again. A reduction in entrainment of gangue minerals in the froth, because you are using was water. In mechanical cells, relatively large size bubbles not favorable in flotation of fine particles, because your selectivity may be lost. In flotation column, relatively small bubbles give higher surface and higher residence times. Actually, in flotation column, you can also control the bubble size distributions much adequately than in mechanical cells. In mechanical cells, no was water is required. A flotation column addition of was water further improves the grade of the product by pushing down the process water containing gangue mineral from going with the product and washing down the coarse gangue particles carried over to the froth by entrainment. This is what I was trying to tell you. The points what I have mentioned there can be easily understood by these two comparative schematics. Like in a mechanical flotation cell, you have got your feed water, and that is your and then you have got this your pulp formation, and here you have got froth water and you have got tailings water. So, there is no was water there. So, you are not able to further clean this froth, so that you can help the entrained particles to be dislodged from that froth phase. Whereas, in the column cell, you see that there is a was water here. So, there are two locations where you are adding water to the system, and this was water basically helps in dislodging your entrained particles and you are forcing them to report to the sink. That is how you are getting a better quality of product. If I look at the evolution of this cell design, these two images, this is the older style mechanical flotation cells, and you see that these are all older styles, and in the next one I will show you what are the modern cells through a video, and it is also downloaded from a open source. You see here, that is flotation cells in the Humboldt mill. These are like your flotation cell, and you see that how they are used to separate the copper and nickel minerals, and you see that they are much more automatic, and you are collecting the froths. The same processes are replicated in a laboratory process, which I had shown you also in the beginning of this flotation lecture, and these small scale tests help you to decide about the right selection of the right kind of your chemicals and their dosages, and then you try to implement it into a modern cell, and the modern cells are much more instrumented. so that you can continuously add your chemical reagents and monitor many other parameters. This is called the science of flotation in our, is a very popular topic. It is as a popular title given in the modern textbooks, but whatever we have discussed, that is also part of the science of flotation, but this should be called the hydrodynamics of flotation process according to me, but I have used the similar term so that you do not get confused when you look at the textbooks. A relatively newer research outcome. The Gorain, that is your name is Dr. Barun Gorain. He did this work in JKMRC, Australia during his PhD. The role of bubble is one of the major components in the science of flotation process. That is, you may have made your materials, your mineral surfaces hydrophobic, but it is the collection of these hydrophobic minerals or the separation between your hydrophobic and hydrophilic materials. They are dictated by that how effectively you have controlled the bubble size distributions, their rising velocities, their stabilities, all sorts of things. So, bubble plays a critical role in deciding ultimately that whether your flotation kinetics is in favorable condition. So, Gorain showed that the first order rate constant K for various industrial flotation cell depends on, let me tell you first, the flotation kinetics is normally modeled by a first order reaction kinetics. Anyway, do not worry about this introductory course. So, and he has shown that the various industrial flotation cell, the rate constant, that is based on which your kinetics of the process basically depends. It depends on feed ore floatability, that is called the P, that is what type of material you are trying to float and what is the floatability characteristics of that. There are various tests, various methods to do that, and you have to test it in the laboratory with a small amount of materials, and that is called the floatability. Then another term he had used, that is called the bubble surface area flux SB, and recovery in the froth phase, that is RF. That is, your material could be hydrophobic, but whether they are actually recovered into the froth phase or not. So, there is a correlation he has developed, and it relates that K is equal to P S B R F. The particle floatability again depends on the degree of hydrophobicity, which is evident what if we understand the basics of flotation, we agree to this. The bubble surface area flux is a key driver within the pulp zone of a flotation unit. That means, how much of what is the surface area of your bubble? Is it lesser than the surface area of your floatable materials or more than that? All this. And the froth recovery describes the froth zone performance. That means, the various issues what I discussed, we had already discussed during the discussion of frothers. So, the bubble surface area flux, how do I calculate it? The bubble surface area flux is the rate at which a bubble surface moves through a cell per unit of the cell cross sectional area. Now, there is again a proposed a correlation, that is S B is equal to 6 J G by d B, where J G is the superficial gas velocity meter per second, and dB is the shorter mean bubble diameter. That is, what are the mean sizes? Shorter mean sizes is again another way of representing the particle size, if you consider a bubble a particle. Now, if we look at the engineering of flotation, now that is the science. Now, how do I engineer it? The industrial flotation practice requires several stages to produce market quality products. That means, in an industrial flotation practice, when we are handling large tonnages of material, only in one stage you can have your targeted degree of separation. So, you have to do it in stages. It is analogous to what we do it in comminution process. Like I want to break the entire material to below 40 micron, the ROM more. I do not charge the entire material to a grinding mill. I first crush it, and that crushing is also at different stages, and then we finally try to do it in a grinding mill. It is also same thing, that you first remove some of the materials, and then you further improve the quality of your product in stages. These stages are combined in various methods. That is, again if we compare it with your comminution circuit, that it can be of different orientations, like your I can have a closed circuit crushing circuit, I can have open circuit crushing circuit, I can have your closed circuit grinding circuit, I can have open circuit grinding circuit, and I can have even your primary grinding and secondary grinding circuit, like your crushing I can have primary, secondary, tertiary crushing, like that. In a flotation also we try to do that. So, these stages are combined in various methods and are called the flotation circuits. How do I decide about this? To do that, first a laboratory test work is carried out before the built up of a circuit for a specific ore in order to determine the suitable reagent. That is, I said that even for an iron ore you can have many collectors, but which collector I should use? So, for that first what you have to do, that is, what is the degree of liberation, what is the liberation behavior of your iron ore. Then you may test the different reagents at different concentrations, and you should see that where the response is the best. Of course, you have to keep in mind the economics also of the process. So, first you have to determine the suitable reagent and the size of the plant, and what should be the tonnages for given throughput and the flow sheet and peripheral data. So, normally what is advocated, what is suggested, that you first go for your laboratory test, and then you go for a pilot plant test, and then you go for a actual your built up of a circuit. Now, again the all three, that triangle if you remember. So, it is not only the chemicals, you have to look at also the your cell design, and you have to, that is the machine variable, and also the process variables like your feed rate, concentration, and all sorts of things. Along with the laboratory test work, another test called pilot plant test work is also carried out in order to determine the continuous operating data for the design, that is planned on the basis of lab test work. And as in a laboratory test work, it is much more controlled condition. Suppose I have to handle only 500 grams of samples, I do not need any material handling equipment. I do not have to worry about the wear and tear of our machines, but and then you are only looking at whether my chemical is appropriate or not. But the kinetics of the process and what is the optimum dose of my reagent. How do I ensure that the mixing of the reagents and the particles are proper at a little bit larger scale in a continuous operation. For that, I have to have a pilot plant test work, the comparison in equipment cost and performance, etc. And you use different types of cells, maybe different types of your peripheral equipment like your conditioning tank, all these, what type of pumps I will require, everything you just optimize it in a pilot based on pilot plant test data along with the performance of your flotation process. The commercial flotation is a continuous practice. The commercial flotations are always continuous one. Cells are arranged in series forming a bank. I will show you that what do I mean by the bank of flotation cells. The pulp enters the first cell and gives some of its valuable minerals in the froth. The overflow from this cell passes to the second cell where more mineralized froth is removed and so on down the tank until the barren tailings overflow the last cell of bank. That means, you try to remove your unwanted material in stages, but along with the material what you try to remove, along with that you are also possibly removing some of your wanted materials, because the appropriate selectivity, appropriate separation in one stage may not be possible, because you have to have a compromise between your economics of the process. So, the residence time you cannot increase because your capacity will go down. So, we do it in stages like your combination, we do it progressive breakage, so that I do not want to generate much more finer particles than what is required. So, here I do not want to lose much of the valuable minerals along with the tailings. So, ensure that I have to do it in stages. We will continue this in next lecture. Till then, thank you very much.